So our Team 5 topic is different types of core layers. We're focusing on the flatten layer, dense layer, and dropout layer. Here's our base model. Based on the base model, we set up the batch size as 64 and epochs as 30, and we didn't use data augmentation. And also we added 2 more convolutional layers at the last. And also we add batch normalization layer after each activation layer. As a result, you can see we have a pretty good test loss and test accuracy. However, we also have overfitting because from the model loss figure you can see that test loss is higher than the training loss. First of all, we're trying to replace the flatten layer as reshape layer. A flatten layer is the layer after the pooling layer. What it does is converting all the results into a single linear vector. A flattened layer flats the input and does not affect the batch size. Flattening step is needed because it can help you use fully connected layers after some convolutional layers. It can be replaced by the reshape function with certain input shape. Here we used 512 as the input shape. Here's the result by replacing the flattened layer as reshape layer. You can see we have a pretty similar accuracy and loss.
The next core layer we are focusing on is dense. Dense is a fully connected layer. A normal CNN architecture always contains repeated blocks of convolution and max pooling layers, then followed by 2 or more densely connected layers. In this lab, we try a plan to replace flatten and dense with global average pooling 2D. Global average pooling layer is used to minimize parameters and restrict overfitting. Other than normal pooling layers, GAP can simply take the average of all values and reduce each feature map to just a single number. This is how we adjust our model. So let's see the result. According to the accuracy line, we can see that GAP really makes a difference in reducing parameters and minimizing overfitting. And besides, it can establish connection between feature map and the category, so it can help to train the model perfectly.
Hi guys, let's continue to different layers. An activation layer means you apply the same activation function throughout the whole layer. By doing that, we can introduce some linearity to a model, which is always necessary. The following 2 graphs shows the performance of a model exactly the same as the original one except all its activation layers. And now we can see without those activation layers, the model is definitely underfitting, which means it lacks the capability to learn some important features from the original data. And it cannot score a higher accuracy, more than 75%. And in comparison with the original 84%, we can see the importance of the activation layers. So, as 2 very common approaches of regularization, dropout and spatial dropout are layers directly inherited from TensorFlow by Keras. And the main difference between them is that while Dropout is just randomly selecting its neurons, spatial Dropout has to define some correlation between its neurons before dropping them out. That means if it finds some strong correlation, like a two-dimensional spatial correlation between neuron A and B, it has to adopt A and B at the same time, or it has to drop them at the same time. And let us see some performances. The picture on the right hand shows the performance of the original model, and the picture on the left hand shows what will happen if we replace all the dropout layers in the original model with spatial dropout layers. As a result, we can see the overfitting situation in the original model is significantly reduced. And the same thing happens with the loss. And this concludes our discussion.